topic of waves, what it is with waves is that there's some elements that are complicated, like what we're doing now. So I like to get you guys to read over everything whenever you can, just to make sure you're up to speed with it, because the next lesson usually has elements of the previous lesson. And so if you guys have done 70 to 80% of the reading right now, we can carry on, yeah? If you haven't done all of the revision or reading, don't worry. I was just using it to give you a reminder of what we done last week. Okay, so last week we looked at refraction and lenses. Now, we looked at two types of lenses. One is convex and one is concave. One technique that's good for you guys, as I'm teaching and I bring up topics, you can try and remember, you can say, okay, what does a convex lens look like? Before Sarah brings it up, I just want to have a mental image of it. And you form a mental image of what a convex lens looks like. Before I bring up concave lens, you think in your head, what does a concave lens look like? And then you have a mental image. And then by the time I bring it up, what happens, your brain's already practiced it once, okay? And then you see it again. So convex, what it looks like is thick at the middle and thin on the outsides. Whereas a concave is thin on the middle and thick on the outsides, okay? So because of these two types of lens, they both do different types of things with light. One of them bends light towards a focus. It bends light towards a central point. The other one spreads light out. It's quite interesting how they work. So we can start looking at that and understanding how they work. So a lens like a concave or a convex lens, a lens that thins at the middle or thickens at the middle, convex or concave, can be thought of as broken up pieces. And we're going to look at that in a second. Hello, Hema, you okay?
Yeah.
Yeah, don't worry, you haven't missed anything. We're just starting now. Okay, so what we do with a lens, let's say we had a convex lens like this. We can break it up into little bits, big fat square in the middle and thinner elements as you get further out, okay? So we have this convex lens and we've broken it up. Each piece is like a prism in a way, it bends light. What's interesting is that the light rays that go through the middle, so imagine light rays are coming to your lens parallel, yeah, they're traveling in straight lines. If they go through the middle of the lens, they go straight through. Anywhere else that these light rays travel through, they'll be bent towards the center. So what you'll get is an image like this, okay? You'll have the lens, the rays of light all going towards a central point known as the focus. This is called your principal focus. The distance between the focus, this point over here where my arrow is, and the center of the lens. The center of a lens, if I got a ruler and I drew it down here and I cut this lens into two, if I split this lens in half, this would be the center of the lens. The distance from the center of the lens, this imaginary line that my arrow is tracing across right now, the distance from this imaginary line to the dot, to where the ray is focused, is called a focal length. It's very important to know that. Some lenses have a long focal length. So some lenses will focus, they'll make this point over here somewhere further. Some lenses have a short focal length. They'll make this point over here somewhere shorter. They'll bend the light more. The more you bend the light, if I bend the light more, the closer it is going to end up to the lens at the focus, okay? So this is something we looked at last week, and I think it's very important that I repeat it once or twice. Okay, so this point is called your focus. The distance between the center of the lens and the focus is known as the focal length, small f, okay? So now, again, this is being, you know, if you were here last week, you'd have had this in notes. If you weren't, I'm going to give whoever wasn't here some extra time later so they can actually go through this again. But does that make sense to you, Hema, that this is the focal length and it's the distance between the focus and the center?
Yeah.
Excellent, okay? So that's a convex lens, okay? Now, convex, it gets thicker at the center. So if parallel rays of light strike this convex lens, you'll see something that happens where they all focus at a central point. What's interesting here is the lens, the ray of light at the bottom actually goes through and ends up in a top position. This ray of light passing through at the top goes through and ends up in a bottom position. The ray of light in the middle stays through the middle. So that's quite interesting. Now, if the rays of light are coming in not parallel, look at what's happening here. They're coming in at angles, okay? You know what this lens is going to do. This lens is going to bend them in some direction. So if they're coming in at some angle, they get bent in a parallel fashion. This is what we said last week. So this is important. Let's look at the top diagram again. If the rays of light are coming in parallel, they get bent towards the center. If they're coming in bent, yeah, like this, they're coming in at an angle, they get turned into parallel rays. So it's interesting. This at the bottom is basically the reverse of what's going on at the top, okay? So if you have diverging light rays, diverging means they come in from different angles, okay? What the convex lens will do, it will straighten them out and make them all parallel. If you have parallel light rays, what the convex lens will do, it will bend them and make them all converge to a single point, okay? So this is what we covered in last week's lesson. We're just recapping it, that lenses bend light in particular ways. Now, some people like Marco, what they do, it's a very smart move. They screenshot the page for later, and other people take notes. It's all good. Both methods are good. Okay, so this is just a recap still. Don't worry too much. So now, let's say I want to find f, this small letter f. We said the small letter f a minute ago. The small letter f represents the distance between the center of the lens, over here, the central line, and the focus, this point over here. This small f, or the focal length, this f, what it represents, the focal length, is a very important concept. When an optician is designing glasses, they pay attention to the focal length of the glasses. So if you have glasses on, if you have a lens in front of your face, let's say, that lens is going to bend light. Depending on how strong or weak your eyes are, that light might need to be bent more, or it might need to be bent less. So this focal length will tell an optician how much bending is going on, okay? So an optician will need to know that to make the right set of lenses match the right set of eyes. Some eyes need a longer focal length. Some eyes need a shorter focal length, okay? Now, if we want to find this focal length, this is where we're going to start today. I first choose a distant object. An interesting thing about distant objects, if I look at an object from very, very far away, what happens, all of the rays of light coming from it will be parallel. So let me give you an example. What I'll do, I'll get my smooth draw application up. So again, we're having a bit of a jumping start into this lesson today, but sometimes it's good to just get into it. All right, so let's say an object is close to me. This guy over here is close to me, yeah? And let's say this guy over here then goes really, really far from me. What this PowerPoint is trying to say, this is my eye over here, let's say this is my eye over here, is that from a distance, what tends to happen is an effect that happens, where all of the rays of light come in parallel, right? So these are the rays of light. If I get very close to an object, what happens, my eye will not only see the parallel rays, but it will also see all of the other rays of light that are coming in. Every object releases light in random directions. So this human being over here releases light this way, then release light this way, then release light parallel, then release light that goes down, then release light this way. But if you get really, really far from it, what's interesting is that these rays of light that are being released in all directions, they don't get to you, they don't get here. Because this one will carry on and go up there. This one will carry on and go up there. This one will carry on and go down there. They won't reach your eyes. Only the rays of light that travel straight will reach you. So this explains why, when you're far from an object, only parallel rays of light would reach you. Because all of the ones at an angle have gone so far away that they'll never get to your eye. But when you're close to an object, let's say my eye was over here. Let's say my eye was over here. Let's say I have a big eye, and it's over here. Pretend this is my eye. I'm going to circle it. Even the bending rays of light, even the diverging rays will reach my eye. As I get further, the effect is that only parallel rays reach my eye. Does that make sense, everybody? I'm going to ask you one by one. So let's start with Ahima. Does that make sense?
Yeah.
Excellent. Does that make sense, Arjun?
Yeah.
Good. Does that make sense, Yasser?
Yeah.
Okay, good. And Marco, make sense?
Yeah.
Okay. So we now know that as you get further from an object, only the parallel rays of light reach you, because all of the other rays have diverged and gone off so far that they'll never get to you. It's like someone kicking footballs. If you're really close to someone, they can kick a football straight at you. They might kick it at an angle. You can still hit it with your foot. You can still put your foot out and grab it. If you get really far from a person, only the footballs that are kicked straight to you will get to you. Anything going off an angle will get too far. Okay? So we're going to use that. We're going to use that to help us find f. So we choose a distant object to get parallel rays of light. We now understand that the distant object will only give us parallel rays. We hold a plain white screen on one hand. So we have a plain white screen, let's say. What you'll find, if you have a lens, so you've got a white screen in one hand and you've got a lens in the other hand. What you're trying to do is you're trying to put the lens between the screen and whatever you're looking at. So the rays of light that are coming through the lens are getting to your screen. So what you have basically is this situation. You have, let me draw another object here. So you don't have to copy anything, it's just an explanation. You have this distant object, let's say it's a building, okay? I'm just gonna draw a rough building. This is your building on some ground. And you have your white screen over here. So again, very rough drawings, just to explain what's going on. This is your screen. And in between the building and the screen, you have a lens. And what's gonna happen here? All of the rays of light that are going parallel are gonna get through this lens. And what are they gonna do when they go through this lens? The one that goes through the middle is gonna go straight to the screen. The one that goes off at angles, what's it gonna do? You guys know, already probably know. It's gonna go like this, make a focal point, and that ray is gonna end up there. This one's gonna go like that, as you know from your previous PowerPoint, and end up there. And then you're gonna have the distance between the lens and the focal point, which is small f, known as the focal length. So that's what we're doing. We're basically looking at an object that's distant, via a lens. We have a screen here from where the lens will take rays of light from the image and then put it onto the screen or project it onto the screen. We know that when you have a convex lens, what it's going to do to parallel rays of light is that the one coming through the center is going to go straight on. The one coming anywhere outside of the center is going to be bent towards a focal point. So the theory that we learned, we should see it being represented in real life. Okay. And again, so if I don't ask you if you get it or not, just put your hands up and ask a question, yeah? It's a very good way to learn, just asking questions. So we have a plain white screen, which we're holding in one hand, and in between the screen and the object, we place a lens, okay? And we move the lens far and away from the screen until an image appears. Now what's gonna happen is this. So if you use a ruler to measure the distance between the lens and the screen, you'll actually get the focal length. It's very interesting how that will work. We're going to talk more about that later. But this experiment here, you don't need it for your exams. It's there to help you understand and get the depth you need to understand this topic. That rays come from an object. When you're far from an object, the rays will be parallel. The object will then take those rays and bend them, and you can create an image on a screen, okay? The distance from the lens to the screen is your focal length. Now, this experiment of how to work out focal length, don't worry about it, but just use this as a way of building up an understanding in your head. You've got an understanding now of how lenses work, okay? What you do need to copy, we'll get to in a bit, okay? So, now, yeah. They do an experiment in some schools in the past to find the focal length. They don't do this experiment a lot anymore, so we can skip that one, okay? Now, we're gonna look at something. Now, this is very important. So, I want you guys to understand one thing. This is your lens, let's say. This is some screen, and you measure the thing. When you bring the screen here, at this arrow, you'll find you make a nice image on the screen. And so the distance between the lens and your screen is your focal length. If I take this distance and double it, I'll get what we call 2f, 2 times the focal length. If I take this distance and measure it on the other side, I have the focal length on this side, and then 2f is double the focal length on this side. So I just want you guys to understand what all of these things mean. What I'm gonna do, I'm gonna give you a diagram, and I'm gonna get you to copy it, okay? So what you're gonna do is just copy this diagram down, please, guys. And when you copy it, I'm gonna get you to add some notes to in a minute. As soon as you finish copying, tell me. After you copy it, we'll label it as well, okay? You okay, Asa?
Yeah.
Good man. If any of you finish copying, just let me know, please. So while you guys copy, I'll tell you a bit of the context regarding this topic. A lot of people don't like this topic because they get confused by drawing something called ray diagrams, which we're going to look at. They get confused by what F means, by what 2F means, by what this line in the middle means. We're going to label it all, and I'm going to explain to you. Have you copied it, Adra?
Yeah.
Okay. So I'm going to minimize it a little bit, and I'm going to leave the minimized version on this side. Okay. Okay. There's some lines there. You guys can ignore them for a minute. What I want to do is actually label some stuff on this, give some extra labeling because it's important, yeah? All right, so on an image like this, I want you to add some labels after you've copied it, guys. I'm just going to draw something similar here on this, on the whiteboard, on my left, on my right, sorry. And here's the line in the middle. Here's your arrow. And we're going to label this slowly now. So this part here represents the lens. So this is representing the lens. And this line represents the central area of the lens. The central, if we have a lens, for example, I'm just going to draw a rough diagram here. Let's say this is a lens. The line going down the middle, this line going down the middle, that's what this represents. We call that the central axis. Central axis of lens. And in brackets, it means the line going down the middle, in simple layman's terms. Line going down middle. Okay. So when you're labeling it, you can talk about that. And then we can add to this, F is going to be, as you know, your focal point or your first focal point. So focal point, this is where the focus is everything. Focal point. So F-O-C-A-L, I'm going to rewrite that because it's a bit rough. Focal point. And you guys already know that the distance between the central axis and the focal point, this distance over here, let me just draw that in, is going to be called your focal length. So I'm going to label that as focal length. And we're going to use black writing to do that, just so we can differentiate between arrows. So that's focal length. Focal length. And we can mirror that. So this length over here, we can have another focal length on this side, or focal point, yeah? So that's also going to be called, this is called F. This is also called F. And if we double that distance, we call it 2F. If we double the distance on this side, we call it 2F. And 2F and F are very important distances, as we'll come to find out in a minute. Okay, so just to recap, here is your lens, central axis, the line going down the middle of the lens. And when light goes through it, it gets focused to a focal point. This is your focal point. The distance between the central axis of the lens and the focal point is known as the focal length, as we can see here. If we double that distance, we call it 2F, or 2 times the focal length. F and 2F on one side, we see the same thing happen on the opposite side. It's mirrored. There's a reason for that. So tell me if you guys want me to leave that on. And if I can move on, I'm going to move on. Yeah. Okay, I want to move on because I feel you guys have copied it. If not, just let me know. All right, so why are these things important? So if I have an object near my lens and it's greater than a distance of 2F, let's say my object's going to be on this side. The light's going to be coming from this side where my arrow is. It's going to be going through this lens and it's going to be focusing somewhere on this side. Now, my lens and my object will have a distance between them. My object can be far from my lens or it can be close to my lens. If my object is greater than a distance of 2F, if it's further out than 2F, this is 2F, object greater than, this sign here means greater than 2F. If it's further than 2F, then something very special will happen. Imagine this is your object, Yeah, this arrow represents an object of this height. So this could be a human. I could have drawn a picture of a box here, a human being, a tennis ball, whatever I want. On these diagrams, they represent the object using an arrow. Okay, it could be anything. What's going to happen from this object? It's going to send rays of light out, and it's going to send rays of light out in all directions, and some of them are going to be parallel. Now, if it's not very, very, very far from the lens, yeah, what's going to happen is that some rays are going to go straight down and through the middle. Anything that goes through the center of the lens goes straight through. Even if it's a ray coming at an angle, it won't bend. You don't see this ray bending or refracting, go straight through. If it came in straight, going like this, where my arrow is, if it followed my arrow straight and went through the center, it would go straight through as well. Anything going through the center of a lens goes straight through, whether it's parallel or it's bent. Now, anything going parallel to the lens gets bent. You know that from before, it gets bent. And what's interesting here is they're just showing you two rays. Look at what happens. This ray that's going through the middle, I'm going to delete that, goes straight through. This ray that's going parallel gets bent, and then they meet up over here. So that's strange, they meet up over here. And then they carry on going. So now this is like a focal point in a way. It's a focus because this is where the rays are meeting up, which is strange. So the thing is, why does that happen? If you're further than a distance of 2f, the bending happens in such a way that it goes away from the focal point. Look at this focus, this is your focal point here. This is where things are supposed to meet. But that only happens when your object is close. When it's further than a distance of 2f, the image, yeah, you'll form an image here. You'll form it between f and 2f. You'll form it between this and this. This is where you'll form your image. If you had a piece of paper, you'd see an image when you brought your piece of paper here. Okay? What will happen, it will be inverted and diminished. What that will mean is this. Look how tall this arrow is. This is the height of the object in real life. But the image, look how tall it is. It's very short. And what's going to happen, the image is going to be upside down. And why it's upside down, we'll come to understand that. It's upside down because what happens, these rays of light end up in opposite positions. You see how this ray of light was on top and this was underneath it? Now, this ray of light goes over here and is actually on top of this one in a way. That's advanced stuff. But all you've got to understand is when an object is greater than a distance of 2f away, when it's further than this distance, it will come out on the other side shorter as an image, and it will come out upside down. They call it inverted and diminished. Diminished means shorter. So you guys can copy this down. As you copy it, copy this ray diagram down, show what's happening. As you copy it, I'm going to ask you one by one if there's any questions. Ohima, are there any questions on this? Is anything confusing?
No.
Excellent. Ajar?
No.
Good stuff. Marco?
You what? Yeah.
Is there anything confusing or are you okay with it?
No, I'm fine.
Good. And Yasser?
No.
Okay. So copy it down, guys. Let me know as soon as you've copied it. I do realize sometimes I go into a lot of detail and explain it over and over again. I only do that to make sure you guys get it. If you want me to explain it more briefly, let me know as well. I can do that. So just draw these two lines. Right, make sure you write this is what happens when an object is greater than 2f away. Yeah. And then what you want to do is show that it's ending up underneath. If you ever have an exam question and they start with an object over here, you now know you need to draw roughly 2 lines to show what's going on the other side. Okay. So I'm going to be honest with you guys. I'm going to tell you that this is the part of physics I probably dislike the most, optics. For some reason, I've never really enjoyed it, but it's got to be done. Some people love it. Okay. I'm going to move on if you guys are okay with it. I'm going to count to 5, and if not, put your hands up or just say you need a bit more time. Or send me a private message. But I'm going to count to 5 and move on if you guys are okay. 5, 4, 3, 2, 1. Okay, cool. So now let's look at this. An object is at 2f. It's not further than 2f now. It's not gone beyond 2f. If you look at this picture here, it's gone exactly onto 2f. Look what happens. We draw those two rays again. The one that goes parallel, we bend it in. The one that goes through the central axis, let it go straight through. What tends to happen here is something very interesting. The object ends up, its image ends up at 2f. So if you had your white screen at 2f, you'd see the image nicely. What you'd find is inverted. It goes upside down because of the nature of the light, because of what's happening to the light, and it's going to be of the same size. So your next diagram, or you can draw it in different colors on the same one. It won't be too accurate though. Your next diagram, you can draw a quick diagram and show this. Okay, or you can write underneath the original diagram that if you have an object at 2f, on the other side, your image will be at 2f, and it will be inverted and the same size. As soon as you do that, let me know. We can move on. I'll give you guys a few minutes, and then just tell me when you're finished, or send me a message to let me know, and then we can move on. Okay, I'm gonna ask one of you guys if you're done, and then we'll see how everyone else is. Audrey, you done?
Yeah.
Okay, excellent. Marco, done?
Yeah.
Excellent. So I'll move on in the next 5 seconds if no one else tells me to wait. Okay, so 5, 4, 3, 2, 1. Perfect. So now we know the image at 2f. What happens if you're at 2f? If you're further, you know it's going to be diminished, smaller in size, and upside down. If it's at 2f, you know it's going to be upside down, the same in size, and also at 2f. Notice one other thing, guys. Yeah, that's that. Okay. If it's between 2f and f, okay, this is the next one. You have your ray of light coming straight and being bent. You have the other one going through the center. Remember, we only need 2 rays of light to talk about this. And what happens, it actually ends up beyond 2f. So the image is formed further than 2f on the other side. So you're coming here closer than 2f. On the other side, it gets further than 2f. When you're at 2f, this is interesting. Give me a minute, guys. I want to show you something. So when you're behind 2f, when your object is behind 2f, over here, when your object is behind 2f, I mix up image and object. Let me start again. So when your object is behind 2f, on the other side, it will be focused, and you'll have your image behind 2f. When your object is at 2f, on the other side, your image will be at 2f. When your image is in front of 2f, on the other side, your image will also be in front of 2f. So when your object is in front of 2f, your image will be in front of 2f. So if you guys get confused thinking, where do I put the image based on the object? Always remember, if the object's behind 2f, image will be behind 2f. If the object is on 2f, image will be on 2f. If the object is in front of 2f, image will be in front of 2f. Now, this gets interesting because if you notice another thing, look at what happens here. When it's behind 2f, it will be short, it will be diminished. It will be shorter than it should be. As you get further, the image gets bigger. As you get onto 2f, the image becomes the same size. As you get beyond 2f, look at what happens. The image gets larger, so you're magnifying it. So objects between 2f and f, your image will be inverted. It will still be upside down, and it will be magnified. So I want you guys to get that down. Keep in mind the patterns you're seeing. They'll help you to remember things. So once you're done, you can tell me, or I'll ask you guys in a second. Let's ask Ahima to start with. Ahima, you done? Can you hear me, Ahima? Okay. Let's ask Yasser. Yasser, you done?
Yeah.
Okay. So if no one complains in the next 5 seconds, I'll move on. Unless you guys want me to keep it on for a second, let me know. No problem. 5, 4, 3, 2, 1. There's also a hand up option on Zoom. So if you feel shy to let me know in front of the others, just put your hands up and only I can see it, and I won't tell the others who said it. I'll keep you guys anonymous if you want that. All right, so 2f and f. Now, at f, something strange happens. So between 2, we've gone behind 2f, on 2f, and between 2f and f. Now let's move to f. At f, what happens is you have the same thing, 2 rays of light we're showing. Now, this is very interesting. These 2 rays of light will go through the object, yeah? But this ray that goes through the central axis, or the central part of this thing, of this axis here, will carry on going, and this ray of light will carry on going at the same angle. These 2 rays will never meet, okay? And it will carry on going and going and going and going, yeah, until the energy of the light runs out, more or less. So they use this in searchlights. What they do with searchlights, they want the light to get as far as it can go, so you can see what's going on. So when they make a light bulb for a searchlight, they put a lens in front of it. And that lens makes the light go out in this fashion. So the light can travel for long distances, and you can see what's going on for long distances. I'll draw a representation of that in a minute, but first I want you to write this down, guys. Okay, so if the object is at F, it will carry on going. I'm going to show you how it will be used in a searchlight in a minute as well. Okay, so I'm going to move on in 5 seconds if nobody complains. Unless you want to tell me, you want me to wait for you, it's all good. 1, 2, 3, 4, 5. Okay, cool. So I assume we've all copied it. Now, this is, let me just tell you a bit more about this one actually before we move on. So this, they said, is used in searchlights, and you might be wondering, how exactly can I put that in a searchlight? Okay, let's have a look. In a searchlight, you have a light bulb, first of all. Yeah, you have your light bulb, you have your torch, and you have your light bulb inside the torch somewhere. So here's your light bulb. Now, the light bulb is going to send light out in different directions. If I can keep a lens at this distance, so imagine this light bulb is your object. So instead of an object, you have a light bulb where your object should be. So let me actually draw that. Here's your light bulb at a distance of f. In front of your light bulb, you're going to have a lens. Yeah? So here's your lens. Now, what's going to happen with this light bulb, you can already kind of see it, is that a ray of light is going to go like this. Let's say if we want to represent it. And another ray of light is going to go right through the center like that. What's going to happen then is your light bulb, your lens, is going to send out this ray for a far, far distance. And so you might be looking for something in the park far, far away, and your rays of light are traveling far. This is your torch light. So what's happening here is that here, you've got, it's the end of a torch. And you know, if you look at the end of a torch, it comes out like this, and it finishes off like this. And this is where your lens is of the torch. If you look at any torch, it's basically this shape. You've got your back of your torch where the battery is, and then you've got your front of your torch, which goes like that. And at the front, there's a lens. And if your light bulb in there is at the distance from the lens of f, what's going to happen, your lens is going to send out rays of light that go very, very far, like that. And you might be thinking, this ray of light is coming out bent. Normally, torches send out rays of light that are straight. What they'll do, they'll in a real torch light, they'll have the light bulb at an angle so that your lens, your rays of light will come out straight. But that's complicated. You just got to know basically that this can be applied to a light bulb. If you keep the light bulb at a certain distance from the lens, you'll get rays of light that travel very far and are parallel and that never meet. And you can use them in a searchlight. Okay, so if any of that's confusing, just let me know. I've never seen a quick exam question on searchlights, but I always like to go in detail to give you guys a solid understanding. Okay, right, so now here, look, this is the focal point. Imagine I put an object in between the two now. If I put an object between the focal point and the lens, right here, what's going to happen then? So there's a lot of diagrams. Now, what's going to happen then, if your object is here, ignore everything on this page. Just look at this blue arrow. If this blue arrow shows an object between F, the focal point, and the lens. What's going to happen to this object? Light is going to come out of it. Yeah, I might have a light in the room somewhere, and what that light's going to do is going to hit the object, and it's going to come off of the object. And therefore, you're going to have a ray of light going straight through the center like this, and other rays of light coming off of the object. So what's going to happen here is, object between F and the lens, you'll have something called a virtual image. At GCSE, they just wanted to know this word. They wanted to know that if you have an object between the lens and the focal length here, what you're going to form is something called a virtual image. Now, the virtual image is formed on the same side of the lens as the object. It's the right way up and magnified. Now, I just want you guys to copy this diagram and copy that down, and we're going to explain a bit more about that, okay? This is an important one. So an object between F and the lens, if you write that down, draw it as they've drawn it. Don't worry about this blue line here. Sorry, oopsie daisy. It's just silly, it's extra, and it's going to confuse you. This is the light source, some light's coming. It's hitting off of the object, and then it's traveling off of the object into the lens, okay? Just understand that and write this down, guys. Okay. I'll give you guys about another 20 to 30 seconds, and then I'll ask. Okay, so I'm gonna count to 5, and you guys can put your hands up and tell me if you still need time. Yeah. So 1, 2, 3, 4, 5. Okay, let me ask you one by one as well, just to make sure. Adrian, you copied it?
Yeah.
Okay, excellent. Marco, done?
Yeah.
Okay. Ohima, you okay? I think-
Yeah.
Yeah, good. Do you understand it, Ohima, so far?
Yeah.
Excellent. And Yasser, you okay? Okay. So now, what we've got to know here is that if you have an object between the focal length and the lens, the object on the object side, what will happen? You'll have an image that's formed the right way up and it'll be magnified. So if you put your eye here, it'll be magnified. The same side of the lens part, ignore it for now because they're overly complicating it. Yeah, and we're going to look at that in a bit. But we've got to know that when you have something between the focus and the lens, you have something that's magnified. It will actually, the lens will make it bigger, and it's what's known as a virtual image. Okay, we're going to look at the same side of the lens and the virtual image, this concept, in a bit. We're going to make sure first we get all the basics. Okay, then we're going to test it out. So now, let's see what time it is. We've got 7 minutes. Okay, so what I want you guys to do is I'm going to do something to this table right now. You might be able to guess what I'm doing. I want to actually delete all of these. I want you guys to just do an exercise, yeah, where we're going to try and put a table down and memorize or put everything down that we know so far. So you've learned some things in your notes here about what's going to happen with the lenses, and you've learned what type of images come out. Some of it you won't be able to fill in because some of it we haven't gone through in detail yet. I want you to fill in as much of this table as you can. So I want you to copy this table down here, everything in it on the rows side and the column side. And where the empty boxes are, where I'm deleting everything, try not to use what I'm deleting. Try not to copy it right now. Where I'm deleting, I want you to fill in the blanks with what you think is right, okay? So there's some stuff in here that we haven't gone through, but through the table we'll understand it. So guys, have a go. Copy this table down and fill in all of the blank bits, what you think should be there, okay? There we go. So object position, greater than 2f, at 2f, between 2f and f, at f, between f and lens. Where's the image going to be? Real or virtual, magnified or diminished, inverted or upright. Erect means upright. So try and do it without looking at your notes even. See how many you can do without looking at your notes, and then look at your notes only for the ones that you forget. Do them in different colors. The ones that you've forgotten, do them in a different color to the ones that you remember. And then you're going to have a good idea of how much you understand. Okay, let's have a go at this for the next 5 minutes. And then we can have a small break or a longer break. Depends on what you guys want.
So can the object position be like at the lens?
The object position can be at the lens, and when it's at the lens, it's so close to the central axis that nothing will really happen. The lens won't do anything to it. If you've ever had a magnifying glass and you've put it close to someone's eye, you notice that when the eye touches the lens, it appears to be the same size. Have you noticed that?
Yeah.
Yeah. So at that distance, there's not enough space for the rays of light to enter and be bent effectively. There is more to that we can talk about later, but it's a very good question. Does that answer your question?
Yeah.
Okay. Good. As soon as any of you are finished, please do let me know. As soon as you finish, guys, let me know. We have 2 more minutes and then we can do a little break.
Done.
Okay, lovely. Okay. So I'm going to start bringing the answers up that I deleted very cheekily. Okay. I want you guys to mark them as you go along or put them in as you go along. Whatever you're not sure about, I want you guys to basically mark as not sure and then ask me where you're stuck. Let me just see this. All right. So there's some things here. Give me 1 second. I'm just going to put this PowerPoint off and reload it because it's being a bit funny with me. Give me 1 second, guys. BoardWorks, physics. Oh, no, we don't want key stage 3. We want key stage 4. And key stage 4 says refraction over here. Okay. Where on earth is it gone? Here we are. So, good. I want you guys to check these answers against what you've done, yeah? So, Ajay, have you marked your answers?
Yeah.
Excellent. Did you get them all right and okay?
Yeah.
Excellent. Marco, how's it going for you?
Good.
Yeah, are you okay with the answers? You understanding it?
Yeah.
Good. Ahima, you okay?
Yeah.
Excellent. Do you understand it?
Yeah.
Okay, wicked. And last but not least, Yasser?
Yeah.
Okay, cool. Do you guys want a break? I'm going to ask you, each one of you, how long you'd like a break for. Let's start with Marco today. Marco, how long would you like a break for?
15 minutes.
Okay, no problem. Ajay?
15 minutes.
Okay. Ahima?
15 minutes.
Okay. And Yasser?
15.
Okay, lovely. So we'll come back. It's 17:18 now. We'll come back at 17:33. Okay. So 5:33. Let's be back and let's carry on with this learning. Good stuff, guys. Well done. Well done. We've got 2 more minutes, guys. We start. Kaboodle, where are you? One more minute. Okay. People. Okay, so let me ask you guys if you're all back. Let's go one by one. Ajay, you back?
Yeah.
Never left? Okay, cool. Yasser? Yasserov? Yasser should be back soon. Ahima, you back?
Yeah.
Excellent. And Marco, I think his internet connection might be a bit funny, so he'll be back in a bit probably. Okay, so what we're going to do the final bits of this now. Because you guys understand lenses to a good extent, hopefully, we're going to look at magnification in a bit, actually. We're going to do a question on this from an exam paper. So we're going to get all of this nastiness out of the way, basically. So we're going to do an exam-based question on it in a second. I'm just going to pull out the mark scheme so you guys can all see what's going on with the mark scheme as well. Let me just make sure this is out and this is out. Okay. Where is my mark scheme? Kaboodle, Excel, Kaboodle. Here we are. And it's P14. And P14 is going to be... Yes, are you back?
Yeah.
Excellent. P14 higher mark scheme. Okay. So what I want you guys to do first is we're going to look at a question and we're going to look at a few more concepts in a second and finish this waves off completely, because waves is more or less nearly done. This was a question we came across a few weeks ago, but I did say to you guys that I want to go over the topic, which we've done today, and then I want to ask you this question again to give you a deeper understanding. Okay, so this is the question. So just, if you want to write down in your notes, practice question on lenses. Yeah, that's your title. Lenses practice question, you can write down on a scrap piece of paper. So let me write down the title here. Lenses practice question. And if you want to know where it came from the AQA paper. Don't worry if you're doing LCR, it's still very useful for you. AQA P14 paper. And the question number is question 3. Okay, so in your little scrapbook of answering exam questions, if you have one, or in your notes, if you're using your notes, this can be your reference and this can be your question here. So let me just get this to the side a bit so you can see a bit more. Okay. So this exam question says, figure 2 is a ray diagram of an object placed in front of a convex lens. Okay, so here is your object here. You guys now know that this middle line represents the lens, the central axis of the lens. You also know that this is F, and this is F, which is the focal length, and the object has been placed slightly beyond F. Okay, what they want you to do is complete the ray diagram to show the position of the image. Okay, so I want you guys to start with that. Draw a rough diagram of what's going on here, and then on your ray diagram, show where the position of the image should be. If your position matches the mark scheme, you're in a good place. Go for it, guys. As soon as any of you are done, please do let me know. And then I'll bring the mark scheme up. You done, Ajur?
Yeah.
Oh, so okay, sorry. Okay, so what I'm going to do, guys, I'm going to bring up the answer. Just think in your head of how you'd answer it, and if the answer matches that, then you're in a good place. If not, then still, it's a learning activity, and we can always look over it again. Okay, so let me bring up my answer. Where's my answers gone? This is, there's a lot of stuff on my screen here. Okay, here we are. There. So number 3, question number 3. Well, it's going to tell you exactly what you should have done. Okay, so it says, you want a ray drawn through the center of the lens. So you should have had a ray drawn right through the center like this. Okay, going on. And then a ray drawn parallel to the lens, like this. Okay. Now what's going to happen, the ray that's parallel to the axis cuts through F and carries on going. The ray that's central through the lens carries on going. So I'm going to show you guys how you draw this, just to make sure you guys have a good understanding. Because sometimes a mark scheme is a bit ambiguous. So let me show you. So here, we're going to draw it here. You've got your line here, you've got your lens here, you've got your object. Your object, if you remember over here, is just a little bit beyond your focal point. So your object is here. So what we do, we draw an object. Let's say this is our focal point. They haven't told us if it's between 2F and F or if it's after 2F. They just told us that our image is here. Sometimes these exam questions can be a bit vague. Okay, so there's your image, or your object, sorry. And this is your focal point. So what they're saying is you draw, and there's this is going to be a focal point here, and this is going to be a focal point here, let's say. The image that goes in parallel, yeah, is going to go, or the ray of light, sorry, that goes in parallel is going to go straight towards it, over here like this. And then as you know, these rays get bent like this through the focal point. This image, or this ray that goes in through the central axis, which is always our second one that we draw, goes straight through. And what's going to happen, they're going to end up meeting somewhere. Yeah, wherever they meet, it's all good. That's all they want you to do. They want you to show that it meets somewhere. Okay, so first of all, let's ask all of you guys, is that what you got? Ajay, did you get that?
Yes, but surely you would know that the object is between F and 2F because it's like 2 squares.
Yeah, that's a very intelligent way to say it. They haven't really specified it there, so it's not easy to see unless you think beyond and you actually use some analysis like you've done there, which is what we were going to mention, but good, you've mentioned it beforehand. Well done. Does that make sense?
Yeah.
Very good point. Ohima, did you get the same type of logic here? Can you hear me, Ohima? Okay, maybe Ohima can't hear, not worries. Yasser? Yasser, can you hear me? Yasser might be a bit busy. Okay, so now we've drawn a ray through the center of the lens. We've drawn a ray parallel to it. We've drawn that they meet up somewhere. And we've drawn where the objects, where the rays cross. Okay. Now, we know when it's between F and 2F, as Ajra has said, well done, you're going to have something that's magnified. So your object, your image is going to be bigger and magnified, yeah? So make sure we know that. And it's also going to be inverted, or upside down, and we know that too. So before I move on, I want to make sure everyone can hear me. Aja, can you hear me?
Yep.
Okay, excellent. Now, so this image that's been drawn, we know from our previous lesson that it's magnified, it's inverted, and it's also going to be something called real. Yeah, those three things we have to know about image. If there's any questions on that, guys, you can tell me if you're not sure. Okay, so we all understand that. Ahima, are there any questions? Let me just see if Ahima can hear me. All right, that's fine. Maybe there's no questions. Okay, let's move on. So the next bit is going to be magnification. All right, I'm going to teach you guys something about magnification now. So magnification is an important concept. We have to learn about it, then we can answer this question. Yasser, can you hear me? There seems to be an issue. Yeah, he can. Okay, cool. Right, so what is magnification? Let me draw this out. You guys can probably already guess what magnification is. While I draw it out, Yasser, did you understand the previous answer?
Yeah, sorry, my mic was having problems.
No problem. No problem. Did you understand what we done though?
Yeah.
Okay. Marco is back from holiday. Okay. Just at the right time. Okay, now, magnification we're learning about, guys. So if you want to write this down in your notes, what is magnification? It's nothing hard. It's just a simple formula. So I'm going to write down the formula first, as they've done in the exam question, and then I'm going to explain it to you a bit more. Marco, can you hear me?
Yeah.
Okay, perfect. Did you have some problems logging back on?
Yeah, I just like, I don't know, my computer switched off, yeah. And then I couldn't get back into the meeting, so I had to do it through like the Zoom website or something.
No problem. Well, you can do, you know, tomorrow when we have a lesson, I'm going to give you a few extra 10 minutes to explain what you missed. Is that okay?
Okay, it's fine.
Okay, no problem. So we're looking at magnification, Marco, this new topic, yeah? Or this new subtopic within waves. Now the magnification, you're looking at how much bigger you're making something. Magnification is a measure of how much bigger you make something through a lens. So we'll write this down, yeah? Because in a lot of exam questions and in a lot of syllabi, they don't explain this properly. Magnification is a measure of how many times larger, or let's use some keywords here, of the enlargement caused by a lens. Caused by a lens. Okay, so the formula for magnification is image height over object height. Yeah, we're going to look at what this means in a second. The definition is magnification is a measure of the enlargement caused by a lens. Okay, so I'm going to give you an example. So imagine you have your object here, your human being. So this is your object. But what I'm going to draw that in red pen maybe in a second. So your human being as an object is here. Object. He's got some height, or she's got some height. You have a lens nearby. And let me just draw this lens. Let's say I've got a lens, just a rough drawing of a lens. That's not even good enough for a rough drawing, that's unacceptable. So here's your lens. Now, what you might have, this human being, you have a ray of light going into the lens like this, and you have it coming out somewhere over there, and then you have this ray of light going through like this, and they cross, and eventually you make an image somewhere, yeah? So I'm gonna draw this a bit bigger. You don't have to draw this, it's just to explain what's going on. It's not gonna be the greatest image in the world, but it's just to explain what's going on, as we said, so you're getting there. And now you might have an image of the person on the other side. And here we have the image, which is bigger. So again, if you're not drawing it, it's just to explain what's going on. This image will have a height. Let's say the image height is 2 meters. Let's say the person's actual height, they're a young person, they might only be 1 meter tall. So the magnification is the image height, which is 2 in this case. So in the example, it's 2 over the image height, over the object height, sorry, which is 1. So that will give you 2. So this is 2 times bigger than that. It's an enlargement here of 2 times bigger than that. Why? Magnification is a measure of the enlargement caused by a lens. This lens is causing this person's image to be enlarged. What's the formula that tells you that? The formula is magnification equals image height So the height of the image that you're forming, which is 2 in this case, over the object height, the height of the object, which is 1. So 2 over 1 gives you 2. This 2 now tells you the enlargement, how much bigger the image is. Does that make sense, guys? I think it does, yeah, but just to make sure. So I'm going to use that now, and we're going to go back to the exam question, and we're going to use the exam question to actually put this into practice, okay? So again, if you need time to copy it, just let me know. Here is the question here, 3.3. I want you guys to quickly just work it out on a piece of paper in your heads, whatever you want. It's all good. Done, Roger?
Yeah, nearly.
Oh, nearly, okay. Let me know when you're done.
Can I see the right one?
Can you see that?
The
Right
smooth
hand.
draw.
Oh, the smooth draw, sorry, my bad.
Thank you.
You're welcome. Let me just put it on for you. 1 second, sorry. Perfect. I want to make it a bit bigger over here. Do you want me to make it a bit bigger?
No, it's fine. Thank you.
Yeah, okay, no problem. There you go. Rahim, are you okay? Rahima's sound's gone. As long as you can hear me, Rahim, it's fine. Marco, did you get it? Did you get what's going on?
Yeah.
Good man, Marco. Yasser? Yasser's microphone's a bit weird, so it's no problem. It's not a problem. Okay. As soon as one of you guys gets an answer, you can let me know. Okay, I'll give you guys another 20 seconds, approximately. We should be getting some numbers out, hopefully. What did you get as your answer, Marco? Did you get an answer, Marco? How about you, Yasser?
Yeah.
What'd you get?
Oh,
Hello, yeah, fine. So I'm just gonna ask Yasser. It's good. Thanks, Marco. What'd you get, Yasser? Okay, and what did you get, Marco? Okay, and what did you get, Ajay? I think the voices are going a bit. Can you hear me, Ajay? If your sound's not working, just log off and log back in maybe, or check your microphones, guys. Rahima, can you hear me? Let me send
hello.
Hello, yeah, Marco. What did you get as your, could you, yeah?
I don't have a calculator on me, but
No problem. Do you know what the method would be?
yeah, 7.5 divided by 3.
Yeah, perfect. 7.5 divided by 3, you give your answer.
So it's 2.5.
Yes, good job. 2.5 times larger. That's your magnification. Okay, well done. All right. So, Ajay, are you okay, Ajay?
Can you hear me?
Yeah, I can hear you now. I can hear
Okay.
you. There's something.
Oh, also, when you write your answer, do you have to put like an X or do you write times?
No, you don't even have to write anything. You can write. I prefer to put 2.5x. Yeah, because when you do magnification, it means you're multiplying it by 2.5 times. So I do 2.5x. It's always better to do that. But in this case, they didn't really ask for that. Okay? Okay, let's move on. So now, question number 4, we're going to do. Question number 4 is interesting. It talks about relationship. We learned about it, to be honest. So look, you've got a lamp box releasing light, and the lamp releases light, and this light goes through your lens. Okay, what your lens does, it releases in all sorts of directions, and your lens focuses this light. Now, a teacher demonstrates how changing the object distance affects the image distance of a converging lens. We learned earlier that the further or closer your object gets from the lens, it affects how far the image is from the lens on the other side. And you've got that in your notes. So what they found was if they have an object at a distance of 32 centimeters from the lens, 28 centimeters from the lens, 24 centimeters from the lens, 20 centimeters from the lens, they find that the distance of the image from the lens is changing. Okay, so what I want you guys to do, or what they're asking you to do, is describe the relationship between the object distance and the image distance. So what I'm going to do, I'm going to take out a bit of this extra writing, and I'm going to bring it all on the same page. Okay, so you guys can see exactly what's going on. So let's take out all of this, bring it all on the same page. Okay, now I want you guys to try and answer 4.1, 4.2, and we'll do 4.3 in a minute. Go for it, guys. I'm just going to make sure, while you do it, I'm just going to do a little sound check with some of you. So Marco, you can hear me?
Yeah.
Perfect. Audrey can hear me because she just had a chat with me. Yasser, you can hear me?
Yeah, hello.
Hello.
Yeah, sorry.
Yeah, well done.
My mic's, you know, it's just
No
still
problem,
buggy.
no problem. You're a good man for having so much patience with your mic. It's good. Ohima, can you hear me? Okay. Ohima's the only one, but I think she's listening, so it's fine. Okay. Go for it, guys. Question number 4. Try and think about what relationship you can see, and then we're going to go through the mark scheme. And then try and think about 4.2, and then tell me what you think. Are you in 4.1 or 4.2? No problem. If your mic, you can even write me a message if your mic's not working. Which one are you on, Marco?
4.1.
Perfect. Yasser?
4.1.
Perfect. And I'm going to go through it in a minute. And Ahima, I think her mic's not working, so don't worry. We'll do it as best as we can. Okay. Give you guys another 10 seconds. Okay, so guys, clearly what we can see here, without even drawing a graph, because they never asked us to draw one, is that if I even model this on a piece of on a smooth draw page, let's look at what's actually happening. So let's say I've got my lens here. Okay, just going to draw a rough lens, and I've got my object, and I'm moving it closer and closer. When my object is at 32 centimeters, so if my object is 32 centimeters away, as you can see here on the box in the exam question, then my image is at 19. So 32 gives me 19. If I then move my object closer, I'm going to draw it in a different color. If I move it to 28 centimeters, which is closer to my lens, then my image is at 21. So you can see 28 represents 21, 32 represents 19. Let's change color again. If my object is at 24 centimeters, then what I'll see is on this side, it will be at 24 as well. If my object is at 20 centimeters, let's draw a different color. Let's use yellow. Okay, if it's at 20, that's too bright, you can't see that. Let's use black. If it's at 20, then also, if it's 20 meters from the lens, then also on this side, it will be at 30. So you can see, the further I am from the lens, what's happening? If you go there, this matches to that, this matches to that, this matches to that, and this matches to that. So the closer you get to the lens, the further the image gets. The closer you get to the lens, the further the image gets. So does that make sense, guys? There's a relationship there. Describe the relationship between the object distance and the image distance. Well, as your object gets closer, your image gets further, okay? So the closer your object gets, the more it gets pushed out on this side. It's like pushing toothpaste through a tube. If I push more and more toothpaste, it gets further and further out on this side. So this is a 3-mark question. So they don't just want one-worded answers. What we're going to do, we're going to look at what we get the other 3 marks from. So if we look, it says, as the object distance decreases, the image distance increases. What we said, that was 1 mark. They are not proportional. Ooh, interesting. The object and the image distance are the same at 24. So notice what we said here. When this was at 24, this was at 24 as well. They wanted you to notice that when things are the same. And they also wanted you to notice that they're not proportional to each other. When 2 things are proportional, so let's look at this answer again actually, before we talk about proportionality. What we can see is as the object distance increases, the image distance increases. That's 1 mark. Yeah, this top bit here. The second mark is where you notice things are the same. And that's hard to notice, to be honest. You'd find it difficult to actually put that into an answer if you didn't know that's what they were looking for. So now that you've seen it once, in the future, you know that they're looking for things that are the same. You can mention that. And they are not proportional. Even that, you'd think, how would I actually know to put that in the answer? Well, now you know. You know, whenever they ask you for the relationship between image and object distance, they're looking at proportionality as well. How do you know they're not proportional? When things are proportional, if you divide one concept by the other, you'll get a number. It should be that number should be the same for all of them. So if you divide 32 by 19, you'll get a number. Yeah. If you divide 28 by 21, you'll get a number. If you divide 24 by 24, you'll get a number. If these numbers are the same, then we have proportional. It means if you change the distance, then if you change the distance of the object, the change of distance of the image is proportional. Proportionality only exists when you divide 2 corresponding quantities and you're getting the same number each time. Here, if I divide 32 by 19, it's not going to give me the same number as if I divide 28 by 21. And that's not going to give me the same number as if I divide 24 by 24. So they're not proportional. This would be very hard to see and know if you didn't know what they were looking for. Okay, so don't slap yourself or don't criticize yourself too much if you couldn't get that. It's a learning curve, and through this we're learning. Okay, so I'm going to move on in a second after I ask you guys if you're okay. Ajay, does that make sense?
Yeah.
Okay, good. Marco?
Yeah.
Cool. Yasser?
Yeah.
Yeah, and Ahim, if your microphone is working, you can say yes or no as well. If not, you can send me a chat message on the chat or we'll carry on. Okay. So now, what we're going to do. Now look, we have the distance of the object. It's all in numbers and those numbers are changing. And the distance of the image, and that's all in numbers and the numbers are changing. So if you have changing numbers on one side, let me write this down. You've got changing numbers on this side. And if you do maths with me, you know the next bit. You've got changing numbers on this side. When numbers are changing, we call that data, someone can interrupt and tell me if they want, we call that type of data continuous. And when you have changing numbers or continuous data, you can make a graph of those numbers on one side. So here we might have image distance on here. And here we might have object distance. Because they're both represented by changing numbers, because object distance is a changing number and image distance is a changing number and vice versa, because they're both changing numbers, you can represent them using a line graph. So if you do GCSE maths with me, if you've done graphs, you'd remember, and even if you do it in school, you'd know if you have values that are changing numbers on both axes, yeah, image is a changing number, object is a changing number, you can have a line graph. And this will probably lead us to our next question. The next question says, suggest a reason why the students were able to draw a line graph of the results and not a bar graph. Because both types of data on the graph involve changing numbers. Or in other words, both types of data are continuous. Whenever we have changing numbers representing data on both axes, on the y and x axis, you know, one of these is going to be on the x axis, one of them is going to be on the y axis, you know that this is continuous and you can draw a line graph. So that's the answer to that question. I didn't even ask you it, just told you the answer to give you guys a reminder. Okay, now, let's do the next question. So you've got this experiment in which you're varying the distance of the object from the lens and you're using that to measure the image distance. So you're changing two things. In every experiment, you want to keep everything else constant because in an experiment, we want to have variables that we're investigating, the one we're changing and the one we're measuring, and everything else should be kept constant so that everything else can't have an effect on your results. In this experiment, what could the teacher have kept constant? I'll tell you a few things just to speed up the process a bit, yeah? And you can think of it while you do it. The teacher could have kept the lamp constant and all of the equipment constant. You could have kept the same screen, the same lens. Because if your lens gets thinner or thicker, what's it going to do? It's going to bend the light differently. And now, if you're bending the light differently, you're not investigating the effect of the distance of the object from the lens. You're going to start polluting it with data on the thickness of the lens. So what you want to do, you want to keep everything the same except what you're changing. Okay. Now, the reason I went through that question quickly or that answer quickly is because I want you guys to focus on this last bit here, which we're going to go to. They've given you an equation out of the blue, 4.4. I want you guys to use this equation out of the blue to try and figure out an answer here. Okay, so 4.4, I'm not going to tell you anything more about it, except that you have to try and do it. Okay, it's a bit of a challenge. Have a go, guys. It's 3 minutes long. Have a go. look at that equation carefully and think about all of the maths you know. And think about how you'd work this out. As soon as you got an answer, you can tell me as well. I'll give you guys another minute and then I'm going to go through it. Okay, at 6:10, we'll go through it. Oopsie daisy, made it too big. Make it a bit smaller. Okay, it's 6:10. Let's go through it. So first of all, they've given us an equation. It says the thin lens equation links the object distance, the image distance, with the focal length of a lens. So just to recap some of these terms, because it's very important that we recap. Here's your lens. Here's an object, whatever it is. Light will go into that object, into the lens from that object. So light will go in here, light might go right through its center, wherever it is. Let's say we've got parallel rays of light. Let's say we've got another ray down here. What this lens is going to do, anything that's parallel, will bend it towards what we call the focus, you see? And anything that goes straight through, it will carry on going straight through, okay? Now, we know this distance between the center of the lens and the focal point, this distance over here, I'm going to put it in red, is known as your focal length. So this is your focal length. You don't have to copy this down, I'll just show you what's going on. So focal length. So this focal length is talking about this number here, 1 over the focal length. The distance of the image, where the image is made, is called your image distance. So how, you know, on this side, if I have a white screen, I can make an image on it. That distance is going to be called the image distance, where your image is actually made. So image distance. So I'm just drawing it very rough to give you a reminder. And this is called your object distance, how far your object is from the lens. So this is how far your object is from the lens. So this is object distance, this thing over here. Okay. So just remember that this equation is telling you 1 over the object distance, 1 over how far the object is from the lens, plus 1 over the image distance, 1 over how far the image is from the lens, equals 1 over the focal length, 1 over this length over here, okay? So now I'm gonna rub this bottom scratching out. Then we're gonna go into the question. Right, now the question says, the lens equation links the object distance, the image distance, and the focal length, as we can see. Calculate the focal length of the lens. Use the data for an object at a distance of 28 centimeters. So look, this is what they want you to do, is this distance here. So at 28 centimeters. So the object is at a distance of 28 centimeters. So already we know that this part of the equation here is going to be 1 over the object distance, which is 28. Okay. Now, plus 1 over the image distance. Well, at 28 centimeters, if you look at the table, you can see, oopsie daisy, that the image distance is 21, clearly here. So the image distance is 21, oopsie daisy. So plus 1 over 21 equals 1 over the focal length. And now from our basic maths, we know whenever you have an equation and you only have one unknown thing, then we can work out that unknown thing. Let's do this side first. 1 over 28 plus 1 over 21. I can do that as a fraction. I can add them together, or I can add them together using decimals. So on my calculator, I'll just do it using a decimal. I put 1 over 28, 1 divided by 28, give me a second, 1 divided by 28, which is going to give us some long number, plus 1 divided by 21. Okay, now that gives me 1 over 12. So these two together, if I divide them, I get 1 over 12. And I might get a decimal as well. That's fine, I don't need it now. Equals 1 over focal length. And 1 over focal length, I can just call this x, because it just represents an unknown quantity. In algebra, we have something unknown, we call it x. I could call it focal length, I'm just going to call it x for simplifying it. Okay, now I want to find out what the focal length is. I want to find out what x is. From my algebra, we know that I can cross multiply this here. So x times 1 is x, and I can cross multiply that one there. Yeah. Or we can use something else, another way of doing algebra, which is, look, I want to, if I multiply this side by 12 from algebra, if I do 12 times 1, then I can multiply that side by 12. But what happens is 12s will disappear. So now this will become 1 equals 12 over x, because we've cancelled the 12 here. We've left that 1, and this equals is there. So 1 equals 1 equals 1 times 12, which is 12 over x. Now, I've got an x here. At the bottom, I want to get the x to the top. So all I need to do is multiply. I can do x times 1 equals 12, or I can say, I can multiply by x on this side and multiply by x on that side. And this x and that x will cancel. This x times 1 will give you x, and that equals 12. So now my focal length, or my x, equals 12. And that is your focal length. Okay, it's 6:15 on the dot. Before we carry on, let me just make, before we finish off actually, let me make sure you guys are all okay. Audrey, do you understand that?
Yeah, well, we're allowed to use a calculator.
You can if you want, because in the science paper you can use calculator. You can do it normally without a calculator as well, but in an exam, I'd say use a calculator just to get it done fast. Is that okay?
Yeah, okay.
Okay, good. And Marco, do you get that?
Yeah.
Good man, Marco. Yasser?
Yeah.
Cool. And Ohima, do you get that? I think Ohima's mic is having an issue. Don't worry, Ohima. What I'm going to do, if your mic's not working, tomorrow's lesson, I'm going to give you some extra free time as well, in case you didn't get anything, and we'll make up whatever you didn't get in that free time. Okay. So do you guys want to call it a day, or do you want to do a few extra minutes? It's up to you guys. Tell me. Ajur, you tell me what you want to do first.
I don't mind, I'm free.
You don't? Okay, cool. Yasser? Yasser's not talking. How about you, Marco?
I'll call it a day.
Call it a day. Okay, cool. What you can do, whoever wants to call it a day can go and relax, and whoever wants to stay on for a few extra minutes and ask any extra questions that they need help with, we can do that. Okay. So whoever wants to call it a day, you can go, and well done. And whoever wants a few extra, Marco, just one thing. Are you there, Marco?
Yeah.
Do you know last Monday's lesson that we had, the one-to-one?
Yeah.
I don't know if just mention to your parents. It might be my account that's the problem. They can check if the money's come through, because last Monday's lesson, I think I might have a problem with my account. The money might not have come through. Is that okay?
Okay. I'll tell them.
It's not an issue. It's not a big issue. Just tell them. Just say Sarah just was wondering.
Okay. Yeah.
Okay,
Yeah.
cool.
Sure.
All right. Good one, Marco. Okay. Good. Yes, sir. Can you hear me?
Yeah.
Okay. Question time. If anyone's stuck on anything, any questions, guys, on anything in science that you need help with? Go on, Ajay.
Why is wave so long?
That's a very good question. Waves is a massive topic. So what we've done over the last few weeks, you'll notice, we've done some of the longer topics. We've done homeostasis, yeah, which was almost 5 lessons. So 10 hours. That was 10 hours. Because homeostasis has so many parts to it. Waves is another one of those topics that has many parts. The shorter topics are those like momentum, for example, and forces to an extent. But we've done some of the longest topics in physics. And so it's good. We've covered it all. And it covers so many different areas. It is long. Any other questions?
No.
No problems. If you have any questions, you can ask. What it is, I would go on to another topic, but what we'll do, if there's no other questions, we will call it a day, okay?
Tomorrow
I'm going to send you the other stuff.
By tomorrow.
Yeah, the options, yeah? And the
Okay, thank you.
Well done. Take care, Salih.
No problem, sir.
Ahima, you okay? Ahima? Okay, I'm going to end the lesson, Ahima, okay? And we'll continue tomorrow. And it should be all good. Take it easy, guys.